Welcome to Math 119, Chapter 7.6, where we talk about inverse trig functions. So in a previous video, we talked a little bit about the introduction of your inverse trig functions, or at least their graphs of the inverse trig and their domain and the ranges. So if you haven't seen that video, please go backwards because we're not going to really be deep diving into these functions and why they are the way that they are. So inverse trig functions are not the same as reciprocal trig functions. So we're talking about like if we were to say, okay, we have your cosine, right? Cosine's reciprocal is secant, right? But secant is not the inverse of cosine, right? So reciprocal and inverse functions are not the same. Instead, recall from chapter 4.4 that inverses are F inverse. So it looks like the one where we have the negative first power. Again, we don't say -1. We just are saying that this is an inverse. So in order to be an inverse, the graph needs to pass what sort of test? Well, this is the horizontal line test. As a result, do sine, cosine, and tangent have natural inverses? So if I were to quickly get my sine, cosine, tangent graphs, here's my sine graph, which I'll quickly put up here. If I can squeeze it in. Here's my sine graph. Let's draw a horizontal anywhere on here. Does that pass my horizontal line test? No, it does not pass. I hit my horizontal line many, many, many times. Okay, well, sine does not have an inverse or a natural inverse. If we do, oops, that was my cosine. If we did the same for your tangent and your cosine graph, I may as well grab my tangent graph on here as well. Here's my cosine. I'm going to draw any sort of horizontal line. Does cosine pass? No, cosine again does not pass. It's going to hit multiple times. We're only expecting to see it hit once. So maybe we have some luck with your tangent. So again, does not pass because we are hitting many times. So if it in fact does not pass, how on earth do we have a whole chapter or a whole section on inverse trig functions? That is because while it doesn't have a natural inverse, we can go ahead and restrict your domain and your range, meaning that we are going to take a small slice of your sine and cosine and your trig. So we'll take a small little sliver of each graph and restrict its domain and its range. Therefore, it will have an inverse. So if we restrict the domain, of the graphs, then it'll satisfy the horizontal line test and be considered a one-to-one function. So notice here that I have this highlighted portion. That highlighted portion is going to be my restriction. So I'm now going to take this tiny little sliver of my sine graph and notice that when I run through this horizontal line, that it's only going to touch my sine graph once, which it should now have an inverse based on that restriction. Same thing here, we're taking this small little sliver before any sort of repeat happens, that horizontal line running through my graph, no repeats happen, we're totally fine. One more time with your tangent, we're just going to take this highlighted portion, and you can see that no matter where you draw your horizontal line, it's only going to be hitting that line once. So that is why your sine, cosine, and your tangent graphs look like this, is that we have taken this little sliver and we have now inverted it. Your x and your y values will then reverse, right? Your domain and your range will also reverse. So see if you can pause the video and determine the domain and range of your sine, cosine, and your tangent inverses. And we'll talk about the name of these inverses here in a moment. So for sine, your inverse, so inverse sine, we can write it as inverse sine of x or of theta, or you can call this arc sine as well, arc sine, or you leave off the E as well. A couple different ways to say it. So your domain here, we're going from -1 all the way to +1. And you do have nice solid dots here, so we are able to include your values. Your y value is going from -infinity all the, sorry, not negative infinity, -π/2 to +π/2. And again, we have solid dots, so we can include these values. Let's do the same for your cosine. Your inverse cosine, so you could say we have inverse cosine of x, or we could say this is arc cos or arc cosine. So inverse cosine has your domain, and notice that we have your x values going from -1 to 1 again right here. -1 to 1. And your range here is going from 0, here we go, 0 all the way to pi. Let's do it again with your tangent. Your inverse tangent, we can say this is tangent inverse of x, or we can write arc tan or arctangent. Again, these are not the same as cotangent or secant, and definitely not the same as cosecant. So these are definitely different than your reciprocal, as we've talked about before. So your domain for your tangent, we're going to be all real numbers. Oh, that's not how we write it. All real numbers. Again, still not how you write it. All real numbers, right, from -infinity to infinity. And your y values, well, these y values are going to be bouncing between π/2 and -π/2. And because these are asymptotes, we are not going to be able to achieve these values. So that's why we have parentheses around here, is because of these asymptotes. Now, when it talks about your inverses, so when we talk about arc sine or inverse sine of x, we're really looking at something like this. So this is inverse sine of 1/2. In order to tackle some of these questions, we need to figure out, okay, well, this is really asking me, what is my sine theta when my sine is equal to 1/2? So this is our coordinate value. And we are searching for your theta. So it just says sine of what value or of what theta, of what degree is equal to 1/2. Well, that would be, again, on your unit circle here, not that one, right here. On your unit circle, can you figure out, well, where is sine equal to 1/2? Well, sine is equal to 1/2 here at π/6. And again, let's see, where else can it be? We're looking for a positive y value. So again, at 5π/6, these other ones are negative, and we are not looking for the negative, but keep in mind your restriction. Your restriction of your sine said we needed to be in between your range from -π/2 to π/2, meaning that is this 5π/6, is that going to be between π/2 and -π/2? No, so this one is a no-go. We're going to be bouncing between these two areas, which means our only option is for sine to be π/6. Now, we're going to be spending a lot of time on that idea of it, so just kind of keep up just for now, and then we'll slow down and practice that idea here just a little bit lower on our page. So let's try it again with your cosine or your inverse cosine of 1/2. So again, this is just looking for, okay, cosine of theta is equal to 1/2. So therefore, what is your theta? Well, this being, again, your coordinate, now your x value coordinate, we are now looking for theta. However, with your cosine, right, we're now looking for cosine of 1/2. So cosine of 1/2, that is at pi over 3. And let's see where else. I'm going to erase that part. Pi over 3 cosine, and that's over at 5 pi over 3. But keep in mind your restrictions when it came to your cosine inverse. We said your range has to be between 0 and pi, meaning that here we have 0 and here we have pi. And this being 5 pi over 3 has now gone past this pi and this 0. So that just means that this one is not going to work, meaning the only place under this restriction for theta to be is at pi over 3. Now, once more with your arctan. So if we're looking for tangent of theta is equal to root 3, again, this is where your tangent, your x and y coordinate, simplified to root 3. So there's only a couple options for this to happen, right? If tangent is y over x, right? We could say, okay, well, this could be when we have 1/2 over root 3 over 2, which if we did simplify, keep, change, flip here, we would get 1 over root 3, which simplified isn't going to come out to root 3. So let's try it again. Now this time with root 3 above over 2 and 1/2 below. So root 3 over 2 times 2 over 1. And notice that you'll get root 3, meaning that we need to find your coordinate that has a positive root 3 over 2 and a positive 1/2, because this is positive. So looking back at your graph here, where is that going to occur? We said, well, when your y value is root 3 over 2, okay, so root 3 over 2, that's right here for your y, so at pi over 3. And again, we want a positive, meaning that we could also have a double negative. So your y value here being root 3 over 2 and your x value being 1/2, again, a double negative will make it positive. So we could have either location, but keep in mind your domain, or your range is going from negative pi over 2 to pi over 2. So this being pi over 2 here and this being negative pi over 2, we cannot exceed this amount and we cannot exceed this amount, meaning that this is not the correct response. So we're looking at strictly for theta to be equal to pi over 3. And again, we're going to get lots of practice here just a little bit further on in example 1. So now let's just get this idea of your domain and range once more and kind of just detail out your graph as to which coordinates, or not which coordinates, but which quadrants we're really looking at. So the solution of the inverse trig is the angle. So notice that we end up with your angle, pi over 6, pi over 3, pi over 3. Whereas we've done it in the past where we're looking for the coordinate. So this is kind of the reverse, which we're talking about the inverse, which is the reverse action. So let's take a look at your domain and range just in a little bit more depth, and you'll see it rewritten out here. Now, when we go to look at your graph, right, as far as your inverse sign goes, we're really looking for your trig function for inverse to be between quadrant 1 and quadrant 4. This being when pi over 2 is above and pi over 2 negative is below. So sign, just think above and below quadrant 1 and quadrant 2. And I should have made this graph just a little tinier because I didn't give us a whole lot of room. There we go. Let me do it again here. Your cosine, it's saying that your range, and again, we're interested in your range here. So for cosine, right, we go from 0. Let me get it a little bit bigger here. We go from 0 to pi, meaning that for cosine, we hover between quadrant 1 and quadrant 2. So cosine, look for your answer to be in either quadrant 1 or quadrant 2. You cannot have multiple answers here for your inverse function. Lastly, when it comes to your tangent, tangent is similar to your sine graph, where we're looking for pi over 2 above and negative pi over 2 below. But maybe I do this in a different color to alert you that, hey, we're actually not going to be able to achieve these values because there is an inverse, not an inverse, an asymptote. So for your answer, we should be in either quadrant 1 or quadrant 4. And we're going to be kind of bouncing in between these two. Let me back up a bit. There we go. Quadrant 1 or quadrant 4. And so we'll be bouncing between these two, but we cannot be at pi over 2 and at negative pi over 2. And again, let me just condense these a little bit to make them a little bit more uniform in size. There you go. So I would draw yourself like a little chart, and then I would put it honest to God in a flashcard just so that you can remember where your domain and your range lies. We're really going to be working with your range when we're looking at your theta. Where is your value? Keep in mind, solution is an angle in the range, which we just spoke upon just that. So let's get some practice when it comes to evaluating your inverse trig functions and state the range. So when it comes to your arc tangent, right? And what I'm looking for here is that some of us, when we go to do these on a test, you're just going to tell me the answer, right? How frustrating that is. I don't want you to just say, okay, well, the answer here is just negative pi over 4. Right? If I just left it at that in my lecture, how on earth did I get this negative pi over 4? Let's say I didn't even touch upon it here, which maybe if you've tracked here, you're pausing the video and that's great, but don't just give me this on a test. I need to know, where did that come from? So as you're trying to show your work, right, think about doing some of these steps. Now, for your inverses, I need you to start thinking about some questions to ask yourself. I need you to ask yourself, where is tangent? Because we're talking about arctan, which is your inverse tangent. So where is tangent equal to -1? And what quadrants are okay? Well, the quadrants for your inverse tangent, we said, well, inverse tangent is going to be your answer between quadrant 1 and quadrant 4. So when we go for our final answer, it should be in either quadrant 1 or quadrant 4. I feel like I've said that word so many times recently, I cannot speak that word anymore. So if we're looking here at a very quick unit circle, right, we're at quadrant 1 and quadrant 4, and we're looking for where tangent is equal to -1. Well, where's just tangent equal to 1? What would that have to look like? Well, in order for tangent of theta to be equal to 1, tangent is y over x. Meaning that, and this is -1, meaning that we have to have the same thing above as it is below. So there's only one location or one coordinate that has the same exact thing, right? So that being at pi over 4 here, that would give us root 2 over 2, and root 2 over 2. Now we need specifically a negative 1, meaning that one of your x and y values has to be negative, right? For us, that can either be in quadrant 2, where we have a negative x and a positive y to give us a negative 1, or in quadrant 4. But we just said, hey, your final answer has to be these two. So if it's not located in quadrant 1, which will this will be a positive 1, it therefore must lie within quadrant 4, where x is positive. And let me scoot this over. And y is negative. Meaning if your y is negative here, this will produce a negative 1. So to dip down, because we cannot go all the way around because your restriction is between, let me make this a little bit bigger to see, is between pi over 2 and negative pi over 2. So if you decide, okay, I'm going to go all the way around my unit circle and I just won't complete it, right? I'm going to go by just under 2 pi, right? Well, your response here isn't 7 pi, not 7 pi, isn't 7 pi over 4, right? That's not our response because 8 pi over 4 is 2 pi and we haven't gone that 2 pi. It's not 7 pi over 4 because that is way too much. It's not following your rules. Instead, to get to your fourth quadrant, instead of going around your unit circle, excuse me as I slowly undo the damage that I've done to this unit circle, in order to get to your fourth quadrant, we're just going to be going in the clockwise direction. Meaning that if we go up to get pi over 4 to give us this coordinate, we can then go down to negative pi over 4 to get our degree. So this is, as we stated at the very beginning, negative pi over 4. So think about doing some of this little detailing as far as, okay, well, what do I know? I have given myself the coordinate. I have given myself what I know about tangent. My quadrants, even better, right? Give me the little stuff. Let's try it again for B. And again, do not tell me on the test, okay, this is equal to 2 pi over 3. You're going to get 1 point for the correct response and then all 4 points off because you couldn't show me your work. Just give me a little bit. So again, ask yourself, where is this time my cosine equal to negative 1/2? What quadrants are okay for my inverse cosine? So our answer should be between 0 and pi, so quadrant 1 and quadrant 2. So quadrant 1 and quadrant 2. So between 0 and pi. So again, I'm going to just draw a really quick unit circle here. So if we need now a negative cosine, theta is equal to x. So we're looking for an x coordinate that has negative, meaning that x is negative over here. So we're either working with quadrant 2 or quadrant 3. But we know we cannot be quadrant 3 because we have to hover between 1 quadrant and 2 quadrant, 0 and pi. 0 here and pi here. So our answer must be in quadrant 2. So where is cosine equal to 1/2? Well, taking your unit circle, right? Well, to get a coordinate of 1/2, root 3 over 2, this must be pi over 3 related. So using your reference angle pi over 3, now to put it over on the other side, we now have 2 pi over 3. So this angle here must be 2 pi over 3, and that is between 0 and pi. It is not 4 pi over 3, not your correct answer. 2 pi over 3. Again, we cannot be 4 pi over 3 because you have gone over your restriction. We can only be between 0 and pi. Ooh. And maybe you do something along the lines of maybe like creating a barrier. So whether that could be like some highlighted portion, again, creating some sort of barrier to say, okay, these are the only values that you can be. You cannot be over here. You must hover between some these two spots. So come up with something that is going to help you visually. Now let's try it again with these two. Now I'd like you to try to pause the video and try these next two yourself. So where is your sine equal to -1/2? And what quadrants are okay for sine? Well, sine, we said, is hovering between quadrant 1 and quadrant 4. So pi over 2 all the way to -pi/2, or vice versa. So I'm going to make my quick unit circle here. So I have pi over 2 here and -pi/2. And I cannot be these two. Maybe instead of highlighting, you don't have a highlighter, maybe just X out those two quadrants. So using what we know, we have a -1/2, meaning that I must be in this quadrant down here in my fourth quadrant. So meaning that my angle, my degree, should be negative. We've gone clockwise. So now let's figure out your reference angle, because this is where your y value is negative, because sine of theta is your y coordinate. So where is sine a 1/2? Well, that is at pi over 6 when we have √3/2 and 1/2, meaning that if I want just the now negative counterpart, I have just gone down below by -pi/6. As far as like, do I have to do all of this work for on the test? You don't have to write the word clockwise. You don't have to do this. I would probably give me a little bit of something as far as like what your domain and range are, or sorry, your ranges. Although I will likely prompt you for this answer, or sorry, for this part. You probably don't need this. So as far as work goes, maybe something along the lines of this chart. Or even ask yourself this sort of question here. So now let's look at cosecant, or your inverse of cosecant of 2. So keep in mind what we know about cosecant. We're looking at, where is cosecant equal to 2? Well, we know cosecant is really 1 over sine. So we're looking at 1 over y. So if we know that for sine, at the very least, we are working with quadrant 1 and quadrant 4. So let's make a quick little chart, little something. Little chart here. We know that these two values are not okay, or these two quadrants. I'm going to give a little bit of something, right? Well, if we have a 2 come up, so if we know that this is 1 over y and this now needs to be a 2, well, we're really looking for how does that 2 come up? Well, that 2 comes up if we have y to be 1/2, right? You can keep, change, flip, 2 over 1 for now 2. So we're looking for where sine is equal to 1/2. And this being positive, we know that just by working with these two quadrants, this is where your y is negative. So we're not working in the negative quadrant, meaning that our answer can only be in quadrant 1. So what is the coordinate, or what is the degree when we have sine of 1/2? Well, that would be at pi over 6. So this is equal to pi over 6. So now let's go and transition to using your calculator. So it says find the degree in radian measure, round degrees to 1 decimal place and the radians to 3 decimal places. Now we're not going to be tested on this as far as like using your calculator. This calculator, or this test, is still a non-calculator test. If that changes, I will let you know. But we're trying to figure out, okay, well, if in the future you were asked to find and evaluate these functions, that you know where to go. Now we'll do these first ones in degrees. So let's take out your graphing calculator. And keep in mind, Desmos, if you want to use Desmos, that is perfectly fine. Maybe I show you once in Desmos that notice that we have this radian and degree. Let's try these degrees first. You're going to go over to your, let's see, your function here. And notice that it has inverse sine, cosine, and tangent. So our first one says inverse tangent, back to your mean, of 20. No, notice that it's about 87.1. And when we flip that to radians, it's about 1.521 radians. So as far as documenting that, let's put degrees here and radians over here. So we had 87.1 degrees, which is about 1.521 radians. Now let's try it again on a different calculator, trying to do arc cosine, so inverse cosine on just a regular calculator. And I might have some junk in there already from a previous class. All right, so let's go first and make sure that we're in a specific mode. So going all the way up to mode, which is located next to your blue second button and under the window button, we're going to go down and flip it to degrees. Let's hit second mode to quit out that screen. And then to get your inverse trig functions, it'll all be in blue. So hit second tangent to get your inverse. Or actually, so sorry, we're going to do your inverse cosine. So second cosine, and we're going to do 4/9. So we get 63.6 degrees. So this is set in degrees. If we wanted to do it again with radians, we just have to go back to mode and switch it to radians. So if I wanted to do it again, and it's now in radians, notice that this is now 1.110 radians. And keep in mind what we figured out, how many radians, like 1 radian is, right? We said that is about 57.3. So 63.6 degrees is just a little bit over 57.3 degrees. It would make sense that your radian counterpart would be just a little bit more than 1 radian. So why don't you try it again with your next one? Doesn't matter which calculator we do. Maybe I do Desmos back again. So I'm going to X all of that. Function, we're doing inverse sine of 1.2. Now notice that this is undefined. Interesting, right? Maybe it's just in your radian. Let's try it in degrees. Again, interesting. It is undefined, but why would that be? Well, it's undefined because look at some of your answers, right? So look at your domain here. Your domain, we said, is going from -1 to 1. These are still your domain values. This is still your, think about like your X values, right? Well, is that going to fit within -1 and 1? No, it's too large. So this is why this is a does not exist or an undefined. It's because it does not fit within your restriction. Whereas your cosine, right, your domain of your cosine was -1 to 1, but 4/9, right, that's a little bit more than a third, right? So it's not, it does fit in your domain. What about tangent? It's 20. Well, your domain for tangent was all real numbers. And that is, in fact, while yes, 20 is much larger than some of these values, you could fit any number in here and it would be all right. So for your next one, arc sine of 0.2, does that fit within your domain? Yeah, it's sandwiched between -1 and 1, so that is going to come out with a true response. Now, if you did that one, it would have come up with 11.5 degrees and 0.201 radians. Now, if the problem does not say degrees, so let's say in the future, it doesn't tell us that on the the problem we want radians or degrees, we are going to always assume radians unless you're going to be given any sort of triangles. Triangles we typically do in your degrees. That is if no units are provided. So let's take a look at example 3. It says a lighthouse is to be constructed half a mile from a long straight reef. In order to ensure that the lighthouse or that the light illuminates certain portions of the reef within specific lengths of time, the engineer needs a formula for theta in terms of x. Find our formula. So if I build some sort of lighthouse, this is my lighthouse, and we have some sort of reef that is a little bit further away, which, how much did we say how far away what this reef was? Well, we said this is a half mile, meaning that the light from the lighthouse needs to get all the way to a certain portion of the reef. This being 90 degrees, we want to assume, or we want to figure out, okay, based on this portion, right? The lighthouse is to be constructed in order to assume the lighthouse illuminates certain portions of the reef. So we're going to put your theta here because we are trying to get this reef being lit upon, right? We want it to be light here. So how far, if we need to, oh, even better. It's just saying find the formula, right? So if this is x here, right? We don't know, they didn't tell us how tall this lighthouse was, but we're just trying to build a formula. So what trig function should be used? Well, we have opposite of your theta, we have an x value. We don't actually know what this value is, but we're just setting us up for a formula. So we have an opposite and we have an adjacent, meaning that your tangent of theta would work really well. We have x over this 1/2 amount, which yes, we will be simplifying to make 2x. And if I said, okay, well, our goal in the future is to determine what this theta is. Let me make that a little bit bigger. I want to know, well, can we solve for this theta? Can we get theta alone? In order to get theta alone, we have to use your inverse trig function, right? Because in the past, we have just been working on, hey, what is your theta? What is this angle, right? Your angle typically goes in here of your function, and then it spits out a coordinate. We're going in the reverse, meaning that we need your inverse function. So 4 theta is equal to the inverse tangent of 2x. And maybe future us wants to know, okay, well, x is now equal to 100 feet tall, right? Then we can figure out, or we want to make sure that everything's in the same unit, right? But we would be able to figure out, okay, given some x value, we can go ahead and get a theta. So we're trying to solve and isolate theta. Now let's try it again with number 4. It says a 50-foot pole casts a shadow. So again, same idea here. We have 50 feet for this pole. It's going to cast some sort of shadow here. Right there. Express the angle of elevation of a function of length x of the shadow. So the angle of elevation, we are looking up from the ground. So we have here, maybe this is us here in that 50-foot pole. We don't have x. We want to find the length of the shadow, this being the length of the shadow. We'll put x right there. And we want to know, okay, well, can we express the angle of elevation? Can we solve for theta? Well, again, we have an opposite over an adjacent, meaning that we can use your tangent of theta once more, 50 over x. And then to get your theta alone, we'll use your inverse tangent of 50 over x. And that would be your final answer, unless they've told us what the length of the shadow is, in which case we could figure out, well, what is theta? As far as this showing up on your test, again, we're not doing any sort of calculators on your test. It would be likely that we are just setting it up. We might even know what x is. Maybe it's even a special right triangle where you could go ahead and evaluate using your skills from what we picked up from this problem or this example one. Now, as far as angle of elevation and depression goes, so if you have some sort of horizon, and let's put this up here so I can give myself a little bit more room. If you have any sort of horizon, when it says the angle of elevation, we're looking above, so kind of peering up at the sky. If the horizon is us being on the ground level, looking all the way up, this would be your angle of elevation. Where if it said, hey, we're now at the angle of depression. Depression means that we are looking down in some capacity. So angle of depression, we look down. So hopefully that makes sense as to what elevation and depression are and to the context of where you might be standing and if appearing up or